Hi students, welcome on in the another lecture on the cylindrical capacitors. So before this I have made another video on the capacitors. So if you do not know the basics of the capacitors, I'll put some videos in the description. You can watch those videos and you can get the idea what is a capacitor. And if you want to know in detail about the parallel plate capacitor, there are the videos on my channel. You can watch those videos. Now here in this lecture, I am going to talk about particularly the cylindrical capacitor. How do we find out the capacitance of this cylindrical capacitor? Basically, like we can have three ways in which we can store the energy or store the charge. These are three basic categorizations. Okay, like one is the parallel plate capacitor that we mostly study. Okay, in that there will be two parallel plates like that. Okay, and then the other kind of could be a spherical capacitor. Okay, other kind of could be a spherical capacitor like this. Okay, which may have a inner sphere and the outer sphere like that, and which will have the opposite polarity of the charges. The other kind of could be the cylindrical capacitor, and this we are going to talk in this lecture. Like there is a cylinder. Okay, now if the shape is kind of cylinder, don't think that it is a cylindrical capacitor. Like usually like in our home appliances, especially like if I take fan, so in the fan there will be a capacitor something like that. Okay, it is not necessarily a cylindrical capacitor. Okay, cylindrical capacitor is that capacitor where the charge is stored on the cylindrical surface like that. Okay, it mean like for example, if I give a positive charge, so then the positive charge is on the inner surface, or maybe you can take it negative, maybe that will be more quite easy to understand. So we have the negative charge on the inner surface of this cylindrical capacitor, and there is an equal amount of positive charge on the outer surface of inner cylinder. Okay, now if the cylinder's radius is like quite okay, these two surfaces are quite very near to each other, in that case it becomes kind of a parallel plate capacitor. Even you can apply the concept of the parallel plate capacitor and you can get the idea from there. Okay, so in the like if I take any kind of parallel any kind of capacitor, there will be like if I take the parallel plate capacitor, so there is positive and negative charge stored like this. If I take a cylindrical spherical capacitor, so there may be positive and the negative charge like that. Now if I take a cylindrical, so then it will be like this. Okay, now there can be sometime a question related to this itself. Okay, the charge distribution. If you want to find out the charge distribution, specifically like when I don't give a equal charge like q and minus q, then in that case what will be the kind of charge distribution? Sometimes it might be confusing. In those cases, if you want to solve the problem, then go with very fundamentals, which are like inside the inside any kind of conductor the electric field will be 0, and second is conservation of charge. Okay, and sometime to do the calculation of the charge distribution, we even apply the Gauss law. Okay, my handwriting is not that good, but I think you can understand what I am writing. All right, so I was saying that yeah, if there is a charge distribution, so you want to find out the charge distribution, then these are the some ways in which you can find out. Just equate the electric field inside to be 0, then conservation of the charge, and then the Gauss law. Maybe sometime it can help. And if you want to know this, like you have some question and you are not able to get it, so then just comment. I will make a video on separately on that charge distribution. How do we exactly get the charge distribution on the different surfaces if we have parallel plate, or we have cylindrical surfaces, or we have spherical surfaces, and sometimes there may be the grounding and all other things with that. Okay, now let's come back to the cylindrical capacitor. In this video we are going to discuss how to calculate the capacitance, and now from this method what I will discuss here, it will also help you to understand How do we calculate the capacitance of any other kind of geometry? Maybe it is spherical or any other kind. Even like I can have a bit complicated, it is not necessarily cylindrical, but I can have a concept. So in that case, if you want to find out the capacitance, there is a method which is similar like this only. Okay, so what the method we are going to discuss, that is kind of fundamental, which will help you to calculate the capacitance anywhere else as well. Okay, so let us go with it. So see, when we talked about the capacitance in the beginning, we say that capacitance is a property of the charge, property of a conductor to store the charge. Okay, and then we define this property C capacitance to be equal to charge stored per unit of voltage. So from there we get this relation C equals to Q divided by V. So if you want to calculate the capacitance anywhere, okay, sometimes you might think capacitance in the terms of capacitance itself. It mean that you might think of breaking the capacitance and then doing the series and parallel, all those things. Okay, and sometimes this formula will help you, Q divided by V. See, like for example, if I take this geometry, if I take cylinder, okay, let me just copy it. Okay, all right, yeah. So like for example, if I take cylinder, if I want to calculate the capacitance, first thing you might think is, okay, why don't we break it as series and parallel? The problem is that in that we don't have kind of like these plates. If there would be multiple plates, then we can break it and in series and parallel, and then we can do it. Okay, like sometime that we will do in case when there is a parallel plate capacitor filled with the dielectric. If I want to calculate the total capacitance, I will apply the series and parallel in that. Okay, but what about here? Okay, yeah, so here I want to calculate. So what I will do is I will calculate the potential difference between these 2 points. Okay, and with the help of this potential difference, I will be able to calculate the whatever the capacitance is, isn't it? Yeah. So what I do for the calculation of the potential difference, little approximations will apply. What are the approximations? Approximations are related to the geometry. Like first of all, we'll consider this cylinder, whatever that is inner cylinder, to be in such a way that it is very long. Okay, or it is comparatively very long. What the meaning of that is, like if I take a radius, inner radius to be equal to A and the outer radius to be equal to B, then this gap A and B is very small compared to this length L. Okay, all right. So if I take this approximation and with the help of that, if I do the calculation, if I want to calculate the potential difference, first I need to calculate the electric field, because I don't know the potential directly. So I will calculate the electric field and then I will apply potential difference. Delta V is equals to negative of integration of E vector dot dr vector. This we learn in the electrostatics, right? So we'll apply this concept, delta V equals to minus of E vector dot dr vector, and we'll integrate it from R equals to A to R equals to B, correct? Now for the electric field, there is a problem. What is the problem? We do not know the electric field because of this cylinder. Do we know? Again, like if we take this approximation, then we know, of course. Do you know what is the electric field because of the infinite long wire at the R distance? So that is 2k lambda divided by R, isn't it? Yeah, so we can apply that. This is the electric field at a R distance. So if I go at a R distance from this center of this, now this much electrical field I will get. And here I will just neglect the negative sign because I know this. I need to take a positive potential difference because the capacitance is going to be a positive property. Okay, so no need to worry about the potential difference, where is the higher potential and where is the lower potential. That of course you can find out if you want to find out the sign, but just we want to calculate the capacitance here. Okay, so yeah, let's find out. So potential difference delta V is equal to 2k lambda divided by r, and let us see the direction of E vector and dr vector. So see, E vector is going to be away from the positive charge, radially outward, as we know the electric field because of the infinite long wire is radially outward, and the dr vector is also in the same direction. So that's why E vector dot dr vector becomes EdR. Okay, so that's why 2k lambda divided by r times of dr. We got that? And now we need to integrate it from r equals to a to r equals to b. Okay, so potential difference, let me do here. So we get delta V is equals to 2k lambda is just a constant, so let us take it out, and 1 by r integration is ln r from r equals to a to r equals to b. Okay, so delta V is equal to 2k lambda times of ln, I can directly say b divided by a. Of course it is ln b minus ln a, which can be written down as ln b by a. So this is the delta V potential difference. I'm just taking a positive value, and now I will apply this formula. And before that, let us do the simplification of this one, because I need to remove the charge q, because capacitance is a property which doesn't depend on the charge, it depends on the property of the material and the geometry of the whatever the conductor is. Okay, so we got this potential difference delta V is equals to 2k and lambda value. So let us place each values here. So 2 times of k is 1 divided by 4 pi epsilon naught, and lambda is q divided by L, and times of ln b divided by a. Okay, so from here of course we'll get delta V is equals to q divided by 2 pi epsilon naught and L times of ln b divided by a. So this is the potential difference in the terms of q. Okay, and now we'll write down C is equals to q divided by V. So that is q divided by V. V is q divided by 2 pi epsilon naught L times of ln b divided by a. So q is cancelled out, and from there we get 2 pi epsilon naught L divided by ln b by a. So this is the capacitance. Okay, for the parallel plate capacitor, this is the formula for our capacitance. Let me just, okay, all right. Now see, in this formula, in the process of the derivation, we got this potential difference delta V, and with the help of that we calculated the capacitance, and this will be the process of the calculation anywhere else as well. So like if you want to calculate the capacitance of this spherical capacitor, this is the way you can calculate. Like if you have a concept, then also you can calculate by this way. Okay, little maybe some complex shape is there, then you can use always this method to find out. Now there can also be the combination of these cylindrical capacitors, right? So that also you can calculate with the help of the calculating the individual capacitance, and then maybe applying the series and parallel by looking at the connection of the plates. Okay, so I hope you must have understood this topic, whatever we have discussed here. If you have further doubts, you can comment, and if you want to get the other topics, any other topic, if you want to watch the videos, and there are the other videos available on the channel, you can share with your friends. Thank you.